We're recording now. Okay. I am pulling out my binders. Almost filled an entire notebook. Okay, so this was from 5.7, 51, and the book's like, oh, hey, now we know inverse trig stuff. Let's do some related rates, and kind of just slides that in there, which is fun for everyone, maybe. Let's see, where's my black pen? Here it is. So 51, 5.7. There are feasibly a couple ways to succeed in this problem. And we'll maybe go through both of them, because I think it helps to illustrate like why we bother with inverse trig derivatives. That could be a fair question. So 51 says, a light is 3 kilometers from a straight beach. If the light revolves and makes 2 RPM, find the speed of the light's beam along the beach at a spot 2 kilometers from the point on the beach nearest the light. Ugh. Well, they are at least kind enough to set us up with a picture. So we have some conception of what's going on here. And we can probably see that there's some sort of triangle in play here. So triangle, related rates, rotation is probably going to involve some trig. Okay. So let's draw our own picture, start jotting down information, seeing what we know, seeing what we want to know, see if we can figure it out. So our picture will look like a triangle. We've got our little light buoy here. And this is 3 kilometers from the shore, straight on. And there's the shore. And this thing is giving off beams of light, but kind of in a straight, it just got one beam and it rotates around. And so we can imagine that it sort of travels at a different speed at different angles. Okay, it's probably going to travel a little faster at these head-on angles. It's going to move pretty quickly, but then it's going to kind of slow down. And so what we want to know is at the moment that this beam hits a spot that is 2 kilometers, what is the speed? Because at any given moment, there's a distance here between the dead-on 3 kilometer beam and wherever the beam is pointed. So we can maybe call that x kilometers. Okay, let's start jotting down variables. It's always our first step after the picture. Let's define some variables. The easiest one, I think, or the most obvious, is x, or actually we'll start with t. T is going to be time. I'm going to go in seconds just because, I don't know, I feel like most related rates problems are usually in seconds. So time in seconds. Because they do tell us at the top of this section, in exercises 49 to 55, use the symbol t to represent time and define the other variables in terms of t. Okay, everything is being defined in terms of t. So that means when we look at x, this distance, X is going to be the distance in kilometers.
Thank you.
You're welcome.
That's fine.
I don't think he was talking to me though.
Yeah, I'm not eating. Yeah.
Distance in kilometers that the light hits from straight point, we'll call that the straight point, light hits shore. I don't know. This is kind of a weird distance to define, but distance in kilometers that the light hits shore from straight point at time t. We're picturing this beam of light as kind of like a discrete moving line. Well, that's not a lot to go on. I think we probably need to worry about this angle in here too. The angle created by the rotation of the light and this fixed, sort of fixed length here. So we're going to call theta theta is going to be the angle between straight beam and current beam, so wherever the beam is, at time t. Cool. I think this is enough to go on now, because now we ask ourselves, what do we want to know? Well, it says, find the speed of the light's beam along the beach. So the rate at which X is changing at the spot that the beam is 2 kilometers from that straight point on the beach. So what do we want? What the heck do we want? We want dx dt when X is equal to 2 kilometers. A big part of these problems is just determining what the heck are we looking for. Okay. It's also important to take stock before we get too far into this problem. Is there anything else we know? Are there any rates? This is a related rates problem, which means rates plural. Is there a rate that we know? And the answer is yes. It's just, I don't know, kind of funky. We know that this light makes 2 revolutions a minute. So we actually know the d theta dt. We know how theta is changing. It's changing at a rate of completing 2 revolutions a minute. We should probably turn that into something a little more useful for us. Maybe turn this into a radian measure, that if we're making 2 revolutions per minute, that means we are rotating 4 pi radians every 60 seconds. 2 revolutions per minute, 1 revolution is 2 pi. Well, we're doing 2 of those in 1 minute. So we're doing 4 pi radians every 60 seconds, which we can then simplify into pi over 15 radians per second. This might be the linchpin of the problem, is recognizing that we do know this rate and being able to identify what it is. So translating the sort of innocent 2 RPM into something a little more useful. Cool. So I'm gonna do this maybe side by side. We do have a couple options here. I forget what step this would be in the step for related rates that we had set up. We need to write an equation. Write an equation and differentiate. To me, the obvious equation to write is something involving the tangent. Something involving the tangent, because the opposite side is this moving quantity, and this adjacent side is fixed. And so let's do option 1 and option 2. So both of these will start in the same place, saying that the tangent of theta is equal to x over 3. And the tangent of theta is equal to x over 3. Okay, so option 1 is just, let's just force this. Let's take the derivative and see what happens. Because this is generally what we would do. We'd set up an equation with some known variables. We'd differentiate and kind of pick up the pieces. See if we get what we need. Let's do that. Differentiating everything with respect to t. And that's sort of a crucial part as well. Everything is being differentiated with respect to t. So, derivative of the tangent is the secant squared. But again, we are differentiating with respect to t. So we get secant squared theta, but then we also need to chain rule out the derivative of theta because theta is dependent upon t. Theta is a function of t. So we spit out d theta dt, which so far doesn't scare us because we know what d theta dt is. The secant squared theta is maybe a little bit worrisome, but we'll come back to that. On the right side, differentiating 1/3 x with respect to t gives us 1/3 dx dt. And oh happy day, dx dt is the WTH we want. We want dx dt. So let's just kind of rearrange this. dx dt, according to what we just did, should be equal to 3 times the secant squared of theta times d theta dt. And so now we look at this right side and figure out, do we know all this stuff? Specifically for x equals 2. Because it's not just dx dt, it's dx dt when x is at 2. Yes, we know d theta dt. Don't know what theta is at that moment, or more specifically what the secant of theta is, but could we figure it out? I think we could, because we know 2 sides of a right triangle, probably find the third, and then use some right triangle trig. So option 1 avoids doing a inverse trig derivative, but it does require you to do some trig, which some of us don't love that. And so option 2 will kind of force us to do an inverse trig derivative, but avoids what we're about to do here, which might be more palatable for some of you guys. But both will work. So we get, at the moment that the beam is 2 kilometers from that straight point, this is a fixed 3 kilometer distance. And so this hypotenuse is 3 squared plus 4 squared, and take the square root of 13. Which means the secant at that moment, 1 over the cosine, well, the cosine at that moment is 3 over root 13. And so the secant that we are seeking is root 13 divided by 3. Just kind of some side work, side hustle, right triangle trig. Because we knew 2 of these sides, we can find the third, use our knowledge of right triangle trig to determine what the secant of theta must be. So now we can just plug all this stuff in, because now nothing is a mystery over here. So the speed at which the beam is changing when x equals 2 is going to be 3 times the secant of theta squared at that moment. Well, the secant of theta at that moment is the square root of 13 divided by 3. And that's squared. And then d theta dt was that kind of the linchpin here, pi over 15. I am going to keep the radians per second here. That'll kind of come into play. Now we simplify. So we get 3 times 13 ninths pi over 15 radians a second. And then how do we want to simplify this? We'll go cancel that. 3. So we get 13 pi over 45. Somewhere along the lines, the radians would have canceled, and we would have gotten kilometers per second. Kilometers per second. We'll come back to this in a minute. Okay, so option 1, we just kind of did derivative, had to do some right triangle trig, but it all worked out. But this is section 5.7, which is all about the derivatives of our inverse trig functions. So we might be thinking, well, why is this in this section and not 3 chapters ago? Well, because now we have the ability to do inverse trig functions, and sort of the benefit of the inverse trig derivatives is that they eliminate the need to have trig functions in our derivatives. So I don't know if you kind of noticed that, but all of our trig derivatives eliminate the trig functions. What do I mean by that? I mean, if you look at all of our definitions, derivative of inverse sine, there's no sine or cosine in here. It's just this inner function. Cosine, same thing. Tangent, cotangent, it's all dependent on this inner function. So that could be a nice thing for us. If we want to sort of just wipe our hands or get rid of the trig situation, the inverse trig derivatives allow us to do that. What do I mean by that? at this first step, instead of going straight to differentiating, we could have turned this into a different equation and saying that, okay, if the tangent of theta is x over 3, well then by definition, that means that theta is equal to the inverse tangent of x over 3. Cool. And now we differentiate this guy. Still with respect to t. On the left side, we get our d theta dt, which is a known quantity. On the right side, we get now the derivative of the inverse tangent, which gives us 1 over 1 plus whatever this guy is squared. So x over 3 squared times the derivative of whatever this guy is. Well, again, we are differentiating with respect to t. This is the tricky moment right here. The derivative of x over 3 with respect to t is 1/3 dx dt, because x itself is a function of t. So when we differentiate x over 3, we have to chain rule. Or basically, we have to implicitly differentiate. Okay, so now we have a way to define dx dt that does not force us to do any right triangle trig. We just have to plug in our value for x, plug in our value for d theta dt, and we should be in business. We should hopefully get to the same spot as we got here, or otherwise that's concerning. So let's clean this guy up a little bit. We'll say that d theta dt is equal to, I'm going to do a couple things at once. I'm going to do 1 over, I'm going to square this, so x squared plus 9, and then I'm going to turn that into 9 plus x squared divided by 9. So I turn the 1 into a 9 over 9, so I combine those things. And then this thing is all being multiplied by 3 on the bottom. The 1/3 kind of gets distributed in there. Still times dx dt. Those, the 3 and the 9 will simplify. So now I've got d theta dt is equal to 3 over 9 plus x squared dx dt. So then finally dx dt, the W2H we're looking for, is going to be equal to d theta dt times 9 plus x squared divided by 3. D theta dt is still pi over 15. X is 2, because that's what we're after. Dx dt when x is specifically at 2. So 9 plus 2 squared is 13. What? That's cool. We get to the same spot. 13 pi over 45 kilometers per second. And we're like so proud of ourselves, and we feel so good about the work we've just done. But we also have this compulsion that we can't be truly happy in our mathematical lives unless the work that we just did, that we're pretty confident about, matches exactly with the back of the book. Because if that doesn't happen, then everything we know to be true is a lie, and your parents don't love you, and the world is headed towards nuclear warfare. So we need to make sure that these answers match the back of the book, or else North Korea pushes the button. 5.7. 51. It's tiny, but no, 52/3 pi, what? We failed. Our lives are meaningless. We should give up. Then we take a deep breath and we see 52/3 pi kilometers a minute. Ooh. We had said kilometers a second. So let's do a quick conversion here. Rami, how many seconds are there in a minute? Should be 60 still. I don't think time has changed. In 1 minute. Little dimensional analysis here. Oh yeah. Get your seconds to cancel. Let's divide some 15s, I guess. There's 4 15s in 60. There's 3 15s in 45. 13 times 4. Oh goodness. 52. It all worked out. Oh man. Okay. North Korea can put the button down. And now we just breathe that deep, satisfying exhale. We did good. And so I took the time to show both of these options because I think lost in the last couple days, perhaps as we sprinted through the inverse trig functions, is why. Like, why do we need them? Shouldn't the regular trig functions be enough? And the answer is that usually, yeah. I mean, I'm not going to say always, because always is a loaded word in math. You can almost always set up an equation with just a regular trig function. It just might lead you down paths that are a little sticky. This might be easier than this. I don't know. To me, it's kind of a toss-up. But as long as you knew what the inverse tangent derivative was, this turns into a fairly straightforward plug and chug. This step right here that we arrived at by just differentiating the regular tangent is still just a plug and chug, but this specifically, the secant squared theta part of the plug and chug, did require a little bit of creativity and extra work. And so it's just a matter of which, at least in this case, which seems the easier path to tread. I don't think there's a right or wrong answer here. I think there's what works for you. So yeah, that was 51. Good stuff. Clarifying questions, 51. So at this point, we've got about 30 minutes. Are there questions lingering from 5.7 or maybe 5.8 homework questions that we want to see me fumble through? Maybe FRQ questions. I'm just opening it all up. This time is yours, and I'm here to help wherever I can. Maybe practice test questions. I just want to sit here and do our homework. Seems to be the vibe in 412, which is fine. Edgar.
35 feet.
Which section? 5.7?
Yeah. I don't know how to get it so that the answer is 0.
Well, let's take a look. Oh Oh, that's nice. That's real nice. Yeah, we're gonna be showing you that for sure. Okay. 5.7, what was the number? 30 what?
35 feet.
35 feet. Yuck. Yeah, let's do it. Okay. There. Good stuff. Next is 33 through 42. Find the derivative of the function. Seems like a simple enough instruction, but then we look at 35 and it's like, yuck. Inverse secant of 5t plus the inverse cosecant of 5t. We can do it though. We're dolphins. Fins up. Nora has a book that's like a high contrast, like one of those cardboard back books. Apparently babies like high contrast because they can actually see it. Their eyesight's still not so hot. And it's ocean friends. And so just each page is like hello to a new animal, but it says it a different way. It's like, howdy seahorse, like, hola jellyfish. And then the dolphin says, good to see you, dolphin. So I don't know why I just thought, oh, because dolphins, fins up. So it makes me happy that it says, good to see you, dolphins. It's always good to see dolphins, especially the Dana Hills variety. Fins up. Just imagine, we could be something truly awful, like a Mission Viejo Diablo. Ugh. You kidding me?
I mean, that's kind of sick, though.
No.
The mask is kind of sick.
Nothing about Mission Viejo is sick, unless we mean it in the literal sense, like it sucks. Okay? Every time I have to drive to Mission Viejo, I'm just like, why?
The turf is good.
Why would anybody choose willingly to live here? It's like you're like 5 miles from the promised land and you just like crapped out on the wrong side of the 5 freeway. Anyway, let's differentiate. So g prime of t inverse secant has a derivative of, and yes, I'm looking this up because I don't have to memorize at this point in my life. Why? I just don't. 1 over, well, let's maybe write this off to the side. No, let's do it. So 1 over u 5t times the square root of u squared, that'd be 5t again, minus 1, times the derivative of 5t, we're going to call 5, plus the derivative of the inverse cosecant of 5t. We're really going to do a minus there because it's a negative derivative. You get minus 1 over u, still 5t, times the square roots. Oh, that's why you get 0, because it just cancels out. But we'll get there. Over 5t squared minus 1 times the derivative of 5t, which is 5. So we get, these 5s are going to cancel. We get 1 over t times the square root of 25 t squared minus 1 minus 5's cancel again. 1 divided by t times the square root of 25 t squared minus 1. That looks a heck of a lot like that thing, which to me means that's 0. Why should that make sense? Beats the heck out of me. But, I mean, does it make sense that those two functions change in sort of an inverse way? Or a cancelable way? I don't know. But the math works out. Cool. When Mrs. Smith and I bought our little condo in San Juan, we literally told our realtor, hey, here's how much money we have. Wasn't very much money. And she's like, oh yeah, okay, cool. Yeah, we can work with that. Like there's like all, like, we can do that. And I was like, wait. It needs to be, and I literally told my realtor that it needs to be south of Crown Valley and west of the 5. And then she like kind of looked at me like, oh, okay, that's gonna be a little trickier. I was like, I don't care. I don't want to live in Aliso Viejo or the weird northern part of Laguna Niguel or Mission Viejo. I want to be south of Crown Valley, west of the 5. Yeah. Location. Anyway. I'm sure there are lovely people that live in Mission Viejo and Aliso Viejo, but not for me.
I don't like those.
Yeah. What else we got?
Can we do 25 from 5.8?
Probably not, but I'll try. 25?
Yeah.
Yeah. Yeah. I'm going to certainly try. The fact that Sheer can't do it, though, does make me a little nervous. He's a pretty sharp cookie. I think that was Sheer that asked. 25 is the definite integral from -1 to 1 of x over square root of 8 minus 2x minus x squared dx. So sort of just like feeling stuff out here. I don't know that we feel great about this being, I'm thinking either inverse sine or inverse secant because of the square root. But let's see what happens. I think my first inclination here is to see what happens if we just try to force a u sub. Sometimes with integrals especially, it's like, let's just try stuff and see what happens. And so if we treat this as x times 8 minus 2x minus x squared to the 1/2, sorry, the -1/2. What happens if we just say that u is equal to 8 minus 2x minus x squared? I don't think this is going to work, but sometimes you try stuff just to confirm that it doesn't work. So then du becomes -2x minus 2. And so dx, sorry, times dx. So dx would be equal to -du divided by 2x minus 2. And that doesn't, well, let's just see. Doesn't feel like that's going to work. Then we'd end up with x times u to the -1/2. Dx is this -du over 2x minus 2. This might kind of work. No. I mean, it sort of feels like that might want to cancel, but I don't think that's our path. Or maybe there's like our partway path. We split this up into No, not seeing it. So let's play around with this inner guy then and see what happens. Let's complete some squares because that seems like a thing that happens sometimes in these problems. Complete square. With negative x squared minus 2x plus 8. We're going to call this negative x squared plus 2x plus something in here plus 8. The plus something I think is going to be a 1, and we got to be careful here that we're going to have this adding 1 is actually a subtracting 1 because of this negative, and so we need to add a 1 to offset that. So again, we added the 1, but it was actually subtracting a 1, and so that we're not throwing off the balance, we're going to add a 1. Cool. So we get the opposite of x plus 1 squared plus 9. Does this help us? Maybe. So let's rewrite this. The definite integral from -1 to 1, x over the square root of 9 minus x plus 1 squared. Doesn't feel that good to me still. We like our stuff. Oh, that looks like something to me. Here's A, here's U. The X is still a little bit worrisome, but we're going to see what happens here. We're just going to wing this and see what happens. We're going to let A equal, so the connection I just made was, oh, that looks kind of like the left side of this guy right here, where our A will be 3, our U will be x plus 1. Am I concerned about the X? Yes. But we will figure that out when we get there. So A is going to be equal to 3. U is going to be equal to x plus 1, meaning that du is dx. So we turn this into the definite integral from -1 to 1, x over square root of 3 squared minus u squared du. Maybe this somehow was the right path. Is this where you've gotten to, Nathan, and felt stumped?
Yeah, I got to negative integral x over x plus 1 squared minus 3 squared. And then yeah, I didn't know what to do.
I'll just stare at it for a second. Sometimes that helps. We messed around with this guy. Let's mess around with this guy. So we get from -1 to 1, x over 2x minus 2 square root of 9 minus x plus 1 squared. Anybody? Anybody do 25 successfully? Let's group think this. Let's think tank this. Come on. 24 brains are better than one. Sometimes. Austin Sierra, no, you may not come in. It's not time for you. What's that? Yeah, I don't know what he's doing. It would be so nice if that X wasn't there, wouldn't it?
Did you sub it for you? No.
We sub it for you. Do like another U sub. And that introduces another variable.
Yeah, probably.
Oh, that might be our answer.
Yeah.
So maybe turning this into x is equal to u minus 1.
Yeah.
Does that help us? Yeah. I don't know if it does. I think that just shifts the problem into a problem with u. U minus 1 over the square root of 3 squared minus u squared du. And then we can maybe break this up into, well, let's see how far this goes. Do -1 to 1 of u over 3 squared minus u squared du minus du over 3 squared minus u squared. So that's nice because this is inverse sine. Then what about that left guy? I think we're kind of just back here. That felt like a good idea. I don't know. I'll have to work on this. Do you guys have a tally going of the number of homework problems that Mr. Smith has not been able to do throughout the year?
Oh, that'd be funny. We
It's
can start with now.
It's probably higher than it should be, but there it is. Yeah, I'll have to get back to you unless somebody's light bulb turns on in the next 9 minutes. If you have no further questions, you guys can take off 9 minutes early since rare is the day that we finish early in here. So practice test is on College Board. We will go over that on Tuesday. Test will be on Wednesday and Thursday. And yeah, have a good weekend. Make good decisions. And we'll see you next week. I think I did post yesterday's, Sandrine, but if not, I will. And I will definitely post today's as well.
Thank you.
You're welcome. Maybe he has a question. Maybe that's why he's here early. Too bad.